on game theoretic probability every 2 years for the last, it has happened 4 or 5 times now. And they have online proceedings where you see slides of talks, and they have all sorts of core game theoretic probability things and links to other things. So hopefully at least one of these connects with sort of what you like. Okay, but sort of you don't have to start out with that straight away. Just sort of at the end of the 3rd lecture, have a look and start thinking about something. Then at the end of the 6th lecture, you need to have a plan. So that will be the 2nd set of 2 weeks. There will be no lectures. So in the first set, we have lectures and homework. There is no homework in the book, so I made up the homework. I put the first set on the webpage yesterday, and the goal of the homework is to make sure that you are not falling behind. So it's forcing you to sort of go through the definitions, apply them a little bit, and think, but not much more. So it's not super hard. It's just to make sure that you're not lost. So that's why I want you to hand them in the next lecture. So you have 2 days for each set. And my estimate of it is that it should take you between half an hour and an hour to make each. So it's not full-time business. Unless you are stuck, but then, I mean, something needs to happen. Good. So, the other thing that I want to say from the beginning is that the reason I taught this course is that I wanted to know what this was about. So, I started reading a few months ago to prepare, and it's just so much fun. So, I really hope that you get this sort of sense of discovery from doing this project. That there is this material that is great and well thought out and exciting and also a little bit challenging, and that sort of you can figure it out on your own. So not on your own, but it will help you get to master it, and that it's sort of fresh and different, in that it's about the same topic as measure theory, probability theory, but it's based on games, and it makes it better suited to some type of brains, I guess. So I'm trained as a logician. I like discrete things, and this resonates very much with that, much more than the measure theoretic probability. Alright, so I hope you experience some of that. Some of the chapters of the book are available online, but only 2 of them are useful for us, because the book has a second half that we won't cover. There is a chapter 1 and a chapter 3, and they are about lecture 1 and lecture 2. For all the other chapters that I'm also covering, thought a little bit about what to do, but I decided in the end that it's crazy to force you to buy the book.
It isn't very hard to find a PDF on it.
Sorry?
It's not very hard to find a PDF on it.
Right, that's great. What's your opinion on this? Because, I mean, so I on the website I said I will make notes for everything that you have no access to if you don't have the book. And I'm still planning to do that. I put the first set up yesterday. But if you both say we have the book and don't bother, then it saves me a bit of work. So
I have the PDF version of the entire book, and if you don't have it yet, I can send it to you.
okay.
Okay.
does save me a little bit of work. Otherwise, you may be able to get it from the library, except that I did, Tom did, and I checked the UvA library and they don't have one. But, and it's nasty because they say they have the PDF, but they won't loan it to you. There's also a system for getting the electronic access. Okay, so in that case, I will be a little bit more relaxed about copying everything over to the notes. Already in the first set, I thought that I could sort of get away with copying not all the book, but as you go along, you figure out it's pretty well put together, and you need sort of most of it. So, okay, good. So let's start with lecture 1. So in lecture 1 I want to do two things. I want to give you sort of an introduction to the principles of game theoretic probability. So this will be something that you need in the rest very much. It's also the basis of the homework. And in the second hour I want to do a little bit of history. So in the end you can entirely fall asleep and not suffer, but if you've ever had some background, it's nice to know how everything fits in. So you'll hear a bunch of big names and sort of a little bit what they did and how it all fits together, and it's sort of a nice back and forth between competing ideas. Of course with this one at the end, the right one. It's all based on the book, so it's what they say. Good. So let's start out with the principles. Also, I guess you guys like a break, right? After 45 minutes. Let's plan that. Alright, so there are two principles that are used in game theoretic probability. And they have been sort of out there before in various forms, but this is sort of the first time when they get put together as the basis. So what are the principles? Well, the first one is called pricing by dynamic hedging. Okay, what does that mean? So, so when you have gambles available to you at certain points in time about, let's say, an outcome that is revealed to you right after you decide on whether you take this gamble. So when you have such gambles, let's call them simple gambles. So when combining simple gambles over time, into complex ones, then the prices for the simple gambles determine the prices of the complex ones. So this is probably sounding pretty vague to you, but the idea is that if you want to say something about what happens over a long run of outcomes, complex gamble, or complex probability assessment if you want, you can do it on the basis of saying simpler things that are not about large numbers of rounds, but let's say just about one round, by getting prices for the simple ones and in some way building up prices for the complex ones. So we'll see much more detail how that works. But this is, you can go from sort of local information to global information. And the second principle is called the fundamental interpretative hypothesis. And it's also called impossibility of a gambling system. Okay, so what is this hypothesis? It says, no matter how smart you are, no way of gambling can do two things for you, namely make you very rich let's say with a reasonable it's a hard choice to get the right word. Let's say chance. And simultaneously, not risk bankruptcy. So it's a hypothesis. It's not a theorem or a mathematical construct, but it's a hypothesis that says no matter how smart you gamble, if the gambles can make you very rich, then they should also be able to make you lose all your money. So together, this is going to be the basis for the theory. We're going to look at gambles, sort of simple ones, make global gambles out of them, and then we're going to relate to the world, sort of what we derived in terms of these global gambles, by saying that, we want to say something about the world, we need to connect the gambles to what happens, and this is where we assume this hypothesis in various degrees of sort of how much we trust it. But the hypothesis will allow us to conclude that some things just don't happen. Alright, so the first bit is sort of a technical machinery that we will develop. The second bit is always something that we think of as optional. Within the mathematics it will never be used. It will only be the bridge that allows us to go from things we derived, things we computed, to statements about the world out there. Okay. So let's make a connection between probability. So how does it happen that probability becomes game theoretic? Well, you can interpret expected values in a probability model as prices. And that will get us started, because now we have these expected values of variables. We look at them as gambles, the variables. We look at their expected value as a price. And then we can start here by saying, if we can have expected values locally for what will happen next, then we can conclude things globally, what will happen in the long run or in infinite runs. Okay, so if you have a probability model, you can instead think of it as generated prices, and you can start there. And you can get a theory from reasoning about the prices game theoretically. So that will be the hedging part. And it turns out that if you look at probability theory, so now this is what researchers write about, say in literature, then you find statements that you can read as the existence of a winning strategy for either the gambler or the world. And so statements in probability are typically about the expected values of some things, but if you make this transformation where you say, okay, let's think of these expected values as prices, let's make global prices out of those local ones, and you look at what such statements say about global expectations, you'll see they have the structure of constructing a winning strategy for one of the players. So this is sort of what the current, what the theory will buy you if you start with a probability model, right? But that would not be super interesting because you'll get the same conclusions. So what is new if you really take the game theory part seriously? Okay, so there are a few things you can do. Namely, you can start from fewer prices. So what does that mean? So if you have a probability model, it turns out you can give a price to any gamble of you as you're choosing. But the theorems may not need all those prices. So in the game theory version, you can sort of reduce assumptions by saying, let's only price a few gambles, and if the strategy only uses those, you get a more powerful conclusion. So you can, in a sense, reduce assumptions. And let's say one more word about this. So one of the ways to reduce assumptions is to say some gambles or some prices are one-sided, meaning that you can buy a gamble at a certain price, but you're not allowed to buy a negative amount or to short this gamble, or however you want to say it, sell the gamble. So sometimes that makes a lot of sense. So that would be one of the typical ways in which you get fewer assumptions. And then you also get weaker conclusions, but they are still useful sometimes. So you get what is called upper prices or lower prices, depending on what happens. Okay. So another thing is that you get stronger statements. Why is that? So probability, if you assume a probability model, you get statements that say, if the probability model governs the data, then this and this and this will happen. So what happens if you go through the transformation to prices and then make a winning strategy? Well, you're still using the prices coming from the probability model, but you don't need an assumption anymore on the underlying process, so the outcomes. So you can the outcomes are generated by an evil opponent. And your strategy, if it's winning, it will still work in that case. So this is one of the things that is very useful for applications. For example, I'm from machine learning, so that will be my core inspiration for applications. But there, you really don't want to use the probabilities as an assumption on where the data come from, because the probabilities are just wrong. They are a model. Maybe it's a good model, but it's not the truth. So if you can assume the probabilities to get prices, but make no assumptions about what the data does, that's a very useful extension. Okay, then there are two more things. So the authors claim that it is cleaner and simpler. I think you have to judge that for yourself, but that's their feeling. And they also like very much the fact that they can deal with open protocols. So here what they are sort of reducing is that in probability theory you typically make a probability measure, and the measure will specify everything that can happen and what probability it has. In game theory, you're thinking more sequentially, which means that you only get prices in the context of where you are now. So given the past outcomes, you maybe get the next price and you're allowed to gamble, etc., etc. But you never have to think about what happened in an alternative universe where the outcomes were different. And I mean, that's sort of typically how things work in the real world. For example, for weather forecasting, doesn't really make sense to ask, like, what could the prediction have been if, you know, back a few days ago you changed something, especially if it's years. You probably will never find out because they developed the software while you were seeing the predictions, and if you these alternatives are weird, and in the game theory they just sort of naturally don't occur. So in probability theory, people are sort of working around this all the time, whereas here, sort of avoided by design. All right. So I want to say one more vague thing and then start new things, or more formal things. So this fundamental interpretative hypothesis, one other way to say the same thing is that an event with low probability is unlikely. This would be a conclusion from a bunch of reasonings, but I'm just giving it away. So, if you want to make a theory about the world, you have to sort of specify what it means for your theory to make statements and check whether the theory is sensible. Right? And this will be the only way in which we can do it. So we can do a computation in theory, we can come up with an event that has low probability in the theory, and then we can say we're going to predict that it will not happen. Or we're going to be very surprised if it does happen.
So unlikely or doesn't happen?
Okay, let's up the math. So if you have an event and you really can show that it has zero probability, then it's normally safe to predict that it will not happen.
Right. Yeah.
But you often are not in this situation. This is only about sort of infinite length statements. If you want to talk about finite experience, you cannot get to this certainty of zero, but you still like to make a statement that says, oh, it was 1 million. So am I now okay to say that it still won't happen? I'm not sort of, how do you say it? My head doesn't explode if it does, but I'm definitely not going to use this theory again.